experiment 10, which is about water and its properties. So this is a couple of labs on water. Water is obviously very important. Okay, so let me remind you a few things. Okay, first of all, water has this shape. So a water molecule is bent like that with two unshared pairs of electrons here. And if you remember from lecture, in a molecule, in a bond like OH, this has a polarity. Remember, atoms further to the right on the periodic table have a stronger attraction for electrons. So that means this bond here has a negative on this side and a positive on this side. This bond does the same. And so that means overall, if we draw a line through here, this side of the molecule is negative and this side of the molecule is positive. So that means water is polar. The molecule is polar. For a molecule to be polar, you have to have polar bonds and you have to have asymmetry. All right, so water is a very polar molecule, and for that reason, water sticks to itself very well. So water sticks to water, and actually, the fact that water is polar is very important. This lab also talks about what are called intermolecular forces. And these are called, I'm just going to abbreviate them IFs. And intermolecular forces are between molecules, so not within. So for example, if I take two water molecules, like that, and I'll draw another one sticking to it, and I'll explain why I'm drawing it this way in just a moment. Okay, whoops, that one's funny. Here, okay, this is an intermolecular force. This is between the molecules here. This is a chemical bond. We've talked about chemical bonds a great deal in this class. Okay, the weakest chemical bond is stronger than the strongest intermolecular force. When you break and form intermolecular forces, that's a physical change. When you break and form these, it's a chemical change. Now, intermolecular forces come in a couple of flavors. Basically, there are what are called dipole-dipole interactions. And a dipole-dipole interaction is when the positive side of one molecule sticks to the negative side of another. So if I draw a molecule like, let's take FCl. Okay, an FCl molecule has a polarity. Remember, fluorine has a higher attraction for electrons. If you're trying to draw the electrons as electron cloud like this is being skewed, where this is the negative side and this is the positive side. If I had another FCl right here, again, right, this is the negative side, the fat part, because the electrons are pulled more that way. That'd be the negative, and this would be the positive. And this interaction here, I'm going to draw with dots, that would be the dipole-dipole interaction, right? So any polar molecules will stick together through dipole-dipole interactions. Let me erase this. Leave those two water molecules over there for just a moment. All right, so that's dipole-dipole. A special case of a dipole-dipole is what's called a hydrogen bond. So a hydrogen bond is a misnomer because it's not actually a bond. It's an intermolecular force. It's specifically when hydrogen covalently bound to O or N sticks to an unshared pair of electrons. In another molecule. So this here is a hydrogen bond. It's a type of intermolecular force. You have the hydrogen, which is covalently attached to oxygen, sticking to an unshared pair. Okay, and then the third type are what are called nonpolar forces. And this is how nonpolar molecules stick together. Whoops. And these are the weakest. All right. And we're not going to go into exactly how they work for this class. So the strength of intermolecular forces would be the strongest are hydrogen bonds. Then dipole-dipole. Dipole-dipole covers a lot of ground because they can be very, very strong dipoles and then nonpolar, or they can be very weak dipoles. All right, so that's a lot of the process, a lot of the stuff this lab deals with. I'm going to break this up. I'm going to go through the background as one video, and then I'll go through the lab itself as another video. All right, so let me erase this, do a little bit more about this. It's a very important concept in chemistry that you're going to see this in part of the lab. You're going to get a lot of data for you because you're not here, so you're just going to have to analyze the data. All right. There's a very important concept because when things dissolve, really why something dissolves, when we have a solution, and we've talked about this before, when you have a solution which is one thing dissolved in another, that one thing is called the solute, dissolved in another. God, I have trouble writing that word. There we go. That thing it's dissolved in is called the solvent. Now, if you think about dissolving things, if I'm going to dissolve something, I'm going to take the solute, it's going to be stuck to itself, right? If I'm going to say I'm going to dissolve salt in water, and then I'm going to, so this would be salt stuck to salt because it's a solid. And then if I put it in water, solvent, stuck to a solvent, right? It's a liquid, so it sticks to itself. And then I get the solution, solute, stuck to solvent. All right, just to show you, if I take sodium chloride, okay, and sodium chloride is Na plus and Cl minus, and this is an ionic compound, and I have water. What determines it is if the bonds that are being broken and the bonds that are being formed, if the energy gained and lost through those processes cancels out. So what happens is, as soon as you mix these together, the water molecules will arrange themselves around the sodium chloride, where the negative side of the water will be around the sodium side, right? Remember, water, the oxygen side is the negative side. I'm just going to draw two here. And the positive side of the water will orient itself around the chlorides because the chlorides are negative. So you see how the water molecules are orienting themselves? And then, give it some time, and you'll have each ion surrounded by water molecules. So that's what happens when you dissolve in an ionic compound. Let's draw another one here. And then for the chloride, I'll try to sneak it in here. You'd have the same thing, but the water molecules would be oriented the other way. Now these dissolve because the types of interactions are basically the same. right? They're polar interactions, and so the difference in strength isn't very much. But you see, and you always need more solvent than you need solute, but this is what happens when things dissolve. In compounds that are polar, that aren't charged, it just breaks intermolecular forces instead of an ionic bond. All right, so there's a very important concept here. Let me just erase. So we take that idea that I'm erasing, you'll find, and you know this from experience when you're cleaning up spills, like say you spill some oil, some cooking oil, or something that's very, I don't know, ionic-y, like water or salt. Just a little bit more than we'll go through the lab itself. All right? It's a very important concept in chemistry that says like dissolves like. And what that means is polar solutes dissolve in polar solvents, and similarly, nonpolar solutes dissolve in nonpolar solvents. All right, and so that's in general an idea. So what that means is that if I have something that's polar, like sodium chloride, it's going to dissolve in something that's polar, like water. Nonpolar solvents are oils. So oils are very nonpolar. And so water doesn't dissolve in oil. If you want to have if you spill oil, you're going to have to use a nonpolar solvent to clean it up. All right, the last piece to this is kind of how soaps work, all right, and also what makes water hard. And I'll keep going on this a little bit. Okay, let me erase this. So soaps take advantage of this idea. Let me show you what a soap looks like. All right, a soap basically looks like this, and you guys have done a lot with structure. Okay, and then there's a bunch of carbons here. I'm going to stop drawing the hydrogens. Just assume there's plenty of hydrogen, and so on. And typically we draw this. Okay, so what's interesting is this part here is very polar. Right, it's even charged. This part of the molecule is nonpolar. So a molecule that is both polar and that is big enough to have different parts is said to be amphipathic. It means it has polar and nonpolar parts. So just to show you how soaps work, okay, if we take an oil, and let's say the oil, let's make the oil red. Oops. How do I do this? Okay, so we say oil, we'll make oil a bunch of squiggles like this. Oils are very nonpolar, they're long chains of carbon. And if we take a soap, let's say the soap looks like this, where this represents the polar part up here and this is the tail. All right, and remember, the oil doesn't dissolve in water. So if we do the oil, what we'll get is this. The oil, if you put oil in water, it does this. It sticks to itself. And then if we put the soaps in there, what the soaps will do is the soap tails are nonpolar, so they'll interact like this. And of course, this is in water, And so water molecules will stick to the soap. Soap's negatively charged, like this, right? And so then if we give this some time, right, you know from experience, if you wash dishes or something, it'll dissolve. It doesn't dissolve immediately. You got to put a little bit of love into it. You got to give it a little elbow grease. And you get this, where the oil molecules are riding piggyback on the soap. This process is called emulsification. So the reason soaps do this is, if you think about why do you use soaps, emulsive, use soaps to take things that are oily and make them dissolve in water, right? This is how soaps work. Now, the last thing in the background is water hardness. Let me just erase one more thing, and then we'll end this video. It's a bit long, I know, but it just is. Just not sure at this point how much background you have from lecture. I don't know where I'll be since we're not actually here. Last thing is what hardness in water. Really refers to a lot of ions, and specifically ions like calcium and magnesium. And since a soap looks like this, the calcium ion will stick to this, and then this will form a solid. This is what a bathtub ring is, all right? And so soaps don't work very well in hard water. Now, what detergents, interestingly, detergents do this. Detergents have a sulfonate. We'll have an O, S, O, 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 then the carbon, and then the long chain like this. The calcium ion doesn't stick to this very well. And so soap detergents work better in hard water. So you're going to look at some of that kind of stuff in the lab. So I'm going to stop the video now, and then I'm going to make a second video for what you're actually going to do, or what you will see done or have data about.